Okay, so we recall we defined the expectation of a discrete random variable taking on one of the possible values a sub I with this number. Okay, and it's provided that it exists. Okay, so so the definition is easy. Now, because we are considering general random variable, so the next question is, how do we give a proper definition of the expectation of a generic random variable x? Okay, question mark here. All right, so we'll try to answer this question in today's lecture. And I will adopt an approach which is tractable, is to consider non-negative random variables first. Okay, so our approach will be like this one. Okay, but to develop an approach for the definition of the expectation of a non-negative random variable, we need simple random variables. So now, a random variable x is called simple if it is discrete and has finitely many possible values. Okay, so simple random variables is a subclass of the class of discrete random variables, because for discrete random variables, the set of all possible values can be infinitely countable, right? So, for example, the value can be arbitrary integers, for example. But for simple random variable, we only consider discrete random variables which has only finitely many possible values. Okay? And such kind of random variable very easy to deal with. Okay, so first of all, I would like to propose a proposition we call proposition 5.2.c for a non-negative random variable x. There exists an increasing sequence of non-negative simple random variables x1, x2, such that the limit of, so for each sample omega, the value, all right, of the nth simple random variables. Okay, so I have to say that because non-negative, okay, is going to approach to the original random variable x, okay, for all sample in the sample space. Okay. So this proposition tells us that for any non-negative random variable, we can construct an increasing sequence of non-negative simple random variables which approach to this non-negative random variable. Okay, so we have a kind of approximation. All right, and the proof actually is by using quantization. So, all right, so we consider a sequence. Okay, so we would like to do some data processing on the measurement result, the x. Okay, so we want to do a sequence of data processing. And each data processing actually is a quantization. Okay, so we will consider a sequence of functions of real value a sequence of real value functions g of n x and from g c. Okay, and the gn, what is the gn? Gn will be, okay, so 0 if x is less than or equal to 0. And it's k minus 1 to the nth power. If okay, so the scale would be the 1 over 2 to the nth power. Okay, so the quantization is like this one. Because we are focused on non-negative values, so for example, for g 2x, for g2 of x, the quantization would be 1/4, because it would be 1 over 2 to the square, the second power, so it's 1/4. So it's 1/4. So this is 1 of 2, 2, 2 of 2, 2, 3 of 2, 2, 4 of 2, 2. 4 of 2, 2 is equal to 1, of course, right? So this quantization, okay, and the bin size would be 1 over 2, 2. Okay. Okay, and so in each bin, right, from the left end to the right end, but not include the right end point, the value will be assigned to the left hand value. All right, for k up to n to the 2 to n's power. Okay, and this is n for all x greater than equal to n. Okay. Okay. So the quantization function you can think about like this one. So let me draw it. Let it G8x. All right. So now it's A. Maybe I use the same 2. Okay. Maybe 2 here. Okay. So okay. So it's 0, and this is 2/4. That is 1/2. 3/4, and this is 1, which is equal to 1, and 5/4, 6/4, 7, and 8, which is equal to 2. And now you have a linear function like this one. Okay, so this is a function that a linear function. Okay, so this is y. So this line is y equal to x, and this is x here. And the quantization number would be here. All right, so for here, we flatter it. Okay, so we do not do any quantization. So this is 0, and this is 0. Okay, and we have open circle up to here, and up to here we have open circle here, and okay, so the value, the corresponding value here is 1/4, 2/4, okay, and from here we have flat, right? We have flat value here. So okay, the value. Okay, so there are only 9 possible values. 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? So in general, the label, they are only n plus 1 label. They are n times 2 to the nth power times plus 1 labels. Okay. Okay, so you have this one. Okay. So this is quantization function. Okay. All right. So this is a sequence of quantization functions. As n goes up, the resolution goes finer and finer, right? Because the bin size becomes smaller and smaller. Okay, and especially you can see that it can be seen that for each x, okay, for all x greater than equal to 0. Okay. Okay, the Gn function, the quantization result, okay, of x as n goes to infinity is equal to x. Okay. And we can see that g1x is less than equal to g2x, less than equal to gnx. Okay, so it's monotone increasing. The monotone increasing property is from the construction, right? Because that as n go up, the resolution becomes higher and higher. Okay. Any questions about the quantization function? Okay. Now, each gnx is piecewise continuous, right? Okay, so you can see piecewise continuous. Now, so define xn, define new random variables to be Gn of x. So what is x of n? X of n is data processing of the random value x. Okay, so we use Gn means that we use quantization, this quantization processing on the measurement result x. Okay, so all right, and by this definition, so by proposition 5.2.b. Sorry, last time I used theorem, but when I look back to our textbook, you always use proposition, so I changed my mind. I'm sorry. So if you the theorem 5.2.a, 5.2.b, the two theorems, please correct them, change them to proposition. Okay. So by proposition, each xn is a random variable. Okay, and it's non-negative and simple, right? Because possible value are n times 2 to the nth power plus 1. So we have only finite to many possible values. Okay, so each xn is a discrete is a simple and non-negative random variable. Maybe I stay it because proposition just tell us xn is a random variable, and xn is indeed non-negative, simple, random variable. Maybe it's better, okay, to describe this fact in another sentence. Okay, any questions? Now, for each outcome in the sample space, we know that G1 x omega is less than or equal to G2 of x omega. Remember, the measurement result is a real number, so it's a little x, right? It's just a real number, a little x. So just a little x for some x on the real line. And so okay. So this is true, right? For everyone. And also limit n goes to infinity, Gn of x omega is equal to x omega, right? So we have these two facts from these two facts directly, because for each outcome we have a real value, because x of omega is a real value, right? Okay, so we have increasing sequence. All right, so this says that. So this says that xn. So the x1 omega less than or equal to x2 omega. Okay, and the limit of xn omega equal to x omega. Okay, and we have done completely. Any questions? We just use the concept of quantization. Okay. Quantization is common practice in communication, because every analog signal will be quantized into this digital signal, and we use digital signal to do digital signal processing every day in your handset, your cellular phone. Every millisecond, now microsecond, have done a lot of digital signal processing in your cellular phone. Okay, when you talk, it's analog signal, and this cellular phone will convert into a digital signal through quantization and the encoding. Okay, and then when we do the digital communication over the air, and your girlfriends or boyfriends or your mother, your parents, your sister, brother, your sibling receive your signal, and their cell phone will convert digital signal to analog signal, and through the speaker they can hear your voice. Okay, so they basically use similar kind of quantizer to do everyday signal processing, including the television, including the web videos, including I am now like maybe my lecture has been recorded and uploaded to the YouTube through the quantization. Is one of the elements through this link. Okay. Okay, so that is okay. Any question? Now, all right. So now we are able to approach a non-negative random variable by a sequence, an increasing sequence of simple non-negative random variables. Okay, so let's investigate some properties of the simple random variables. So, so proposition, before we investigate the expectation of non-negative random variable, we will investigate some properties of expectation of simple random variables. All right, so proposition 5.2.d. Okay, so let all right, so let x and y, okay, be two simple random variables, not necessarily non-negative, just simple only. Okay. First, if this simple random variable, this is non-negative, then the expectation of x, okay, must be non-negative too. Okay. Second property, expectation of ax plus by. So the sum is equal to the expectation of x, a times the expectation of x plus b times the expectation of y, for all a, b in the set of all real number. Third one, if I'm sorry, if x is less than equal to y, then the expectation of x would be less than equal to expectation of y. Okay. Fourth one, if you take the absolute value of the expectation of x, then it will be less than equal to the expectation of the absolute value of x. Okay. Fifth, if x and y are independent, okay, I define independence on two discrete random variables before, right? In chapter 4, i.e., maybe I need taking value in AI and bj up to m. Maybe I specifically respectively. Okay. All right, so I explicitly give the possible values for this simple random variable x and possible values bj for simple random variable y. Because I want to remind you what do we mean. That means that if you okay, if you have the probability of this joint event, okay, is equal to the product of respective event. Okay, so that is the definition. It's very simple. Okay, you can go back to look for the definition of independence between two discrete random variables. Okay, so just here, okay, arbitrary. So if x and y are independent, then the expectation of their product is equal to the product of their respective expectation. And the last one, the expectation of the absolute value of their product, and take the square, would be less than equal to the expectation of the x square times the expectation of the y square. Okay. Okay, which is called Cauchy-Schwarz inequality. Okay. Alright, so there are 6 simple properties about expectations of simple random variables. Okay, so show it. So by definition, the expectation of x is the sum of I from 1 to n ai, and the probability of x equal to ai. And expectation of y is the summation j from 1 to m, bj, probability of y equal to bj. Okay, so that is directly from our original definition of expectation of discrete random variables. That we have finite sum because that we have only finitely many possible values. Okay, so the sum always exists and is finite. Okay, it's finite. That's why it's x and y are called simple, because you can investigate their property in some elementary way. Okay, so the first one, of course, if so if x greater than 0, then ai will be greater than equal to 0 for all I from 1 to n, right? This is definition of non-negative because its values always non-negative. So each ai should be greater than or equal to 0. That's definition of non-negative random variables. Okay, so this is non-negative, and the probability always non-negative, right? So and obviously expectation of x, which is greater than equal to 0. Okay, so the first property x, very simple, right? So if x is a non-negative simple random variable, then its expectation must be non-negative. Second, okay, second would be so okay. The proof. Okay. Okay. We can represent x and y by in the follows. Okay, so x is actually summation of I from 1 to n and ai, and the indicator of the event x equal to ai. And the y can be represented ai on bj indicator of y of bj. And the reason is that okay, okay, so let me explain that. If x omega is equal to ai, right? Then the indicator of x equal to ai omega is equal to 1. Okay, because that if this event occur, okay, then in the indicator is equal to 1. Okay, and the indicator of x equal to a I prime omega is 0 for all I prime not equal to I. Okay. So summation for I from 1 to n. Oh, maybe I use k with beta. Okay. I not equal to k. So the ai indicator x equal to ai omega becomes to ak. Okay, and so this is equal to x of omega. Okay, so that's proof that they are equal. Okay. Similarly, if y omega is equal to bk, then indicator of y equal to bk of omega is equal to 1. And maybe I use but indicator of y equal to bj omega equal to 0 for all j not equal to k. So that the summation j from 1 to m and the bj indicator y equal to bj will be equal to bk. Because the indicator, oh, I forgot to put omega. Because only when j equal to k, this is 1. For j not equal to k, this is 0. So we have bk. And this is just equal to y of omega. Okay. Okay, so that this is the representation. So we can use the indicator to represent a simple random variable. Okay, so now ax plus by becomes to a summation I from 1 to n ai indicator x equal to ai plus b summation j from 1 to m and bj indicator x equal to y equal to bj. Okay. Now since for each I, this is equal to intersect of the disjoint union of y equal to bj. Okay. This one is equal to the sample space. As we know that they form a partition of the sample space. Because every so that so this is sample space, and so x equal to, so the event a1, x equal to a2, x equal to an. Okay, so that is the one partition, one possible partition, right? By using so this is atomic event, right? For simple random variables x. Okay, so they are the smallest possible non-empty event can be specified by the simple random variable x. And similarly, you can use y equal to b1, and this is y equal to b2 up to y equal to bm. Okay, so now you can use atomic event generated by simple random variable y. Okay, so I just deliberately write it vertically. Okay. All right. So this event intersect with the total event will be the same. Okay. And so that by De Morgan's rule, we know this is the disjoint union of x equal to ai intersect y equal to bj. Okay. Right, and usually we will write this joint event as x equal to AI and y equal to bj. Okay, and so now the indicator of x equal to AI becomes to the sum of the indicator of x equal to AI and y equal to bj. Okay. So you can think about that in each vertical, because each vertical strip corresponding to one atomic event generated by x. Okay, and we can divide this vertical strip by horizontal strip, right? So into m parts. Okay, into m parts. And so the indicator of this event, okay, become the sum of the indicator of the smaller event. And because these small events, they are disjoint to each other, so they become to one, cannot simultaneously, right? Only one of them can be one only. Okay, so this is become to sum. You can check that. Okay. Okay, similarly, the indicator of y equal to bj become to the sum from I to 1 to n, indicator of x equal to AI and y equal to bj. Okay, so now ax plus by becomes to a summation I from 1. So I will write it ai and summation j from 1 to m, indicator x equal to ai, y equal to bj. Okay, because I use this identity plus summation j from 1 to m, bj, summation I from 1 to n, indicator x equal to ai, y equal to bj. Now, because they are finite sum, so I will write it. Okay, so now we merge together. So we have ai 1, x equal to ai, y bj, indicator, plus summation I from 1 to n, j from 1 to m, and bj, indicator x equal to ai, y equal to bj. Now, they have the same, you can see the indicator. So we can merge them. ai plus bj together, and this is indicator x ai, y equal to bj. So which shows that ax plus by is a simple random variable with possible values in where in the set AI plus Bj for I from 1 to up to n, j from 1 to up to m. Okay, and this size at the most n times m, right? But maybe some of the sum will collide, will be the same. So the size may be smaller. Okay, so whose size is less than or equal to n times m. Okay, all right. So so the indicator notation give us a way simultaneously to show that the linear combination of two simple random variable is still a simple random variable. Okay, even though I didn't state it here explicitly, but we have to make sure that. Okay, and possible atomic events are the smaller pieces here. Okay, so that each small piece will be possible atomic event. But if they corresponding to the same value, then these two pieces will be joined together. Should join together. Okay, because they have the same value. Okay. Any questions? Okay, so once we know that this linear combination is a simple random variable, then its expectation, then by definition, the expectation okay, become to sum AI plus Bj and probability of x equal to AI, y equal to Bj. Because that when x takes this value, y take these values, then it so that in this event, so the probability, because in this event the value will be a times AI plus b times Bj. Okay, so the weighting, so we weight this probability. Okay, so we have this one. Is that okay? You can come see here the expectation, as we just okay, and y okay. So that means that the x takes value AI in this event, Okay, and this event occurs with probability here. Okay, so that this is weighting sum. So the value is AI, but the random variable has its value with this probability. Okay, so this is corresponding to the probability of this event, and so similarly, if we express sum of, so this is the value for all the sum outcome with this pair of values. So in this event, for all outcomes in this event, the value of this linear combination is this sum. Okay, so we have the, okay, all right, and so now we will separate them. So now the rest will be easier. And this is A is a common, and the AI depend only on I, and the summation J is for, okay, plus summation J from 1 to M, or B is a common vector, so we move it out of the summation, and this is BJ is here, and the I dependence. Okay, but this one, okay, so this is the summation probability of x equal to AI intersect y equal to bj. Okay. And this is the probability of the disjoint union x equal to AI intersect y equal to bj. Okay. And this is the, by De Morgan's rule, intersect the union J from 1 to M, y equal to bj, and this is probability of x equal to AI intersect the total event, and this is the probability of x equal to AI. Okay, all right. So this part is here, and similarly, this one is equal to probability of finite sum over all AI. So it's just what? Just the decomposition formula, right? In chapter 2, oh no, chapter 3, we have decomposition formula. Okay, because y equal to bj become to a partition of the total event, the sample space. So this is x. Oh, I'm sorry. X equal to AI become to a partition. So this is becomes true. Y equal to bj. All right, so this is come to summation I from 1 to n, AI probability of x equal to AI, plus B summation j from 1 to m, bj probability y equal to bj, and this is A times expectation of x plus B times expectation of y. Okay, so we have done. So at the beginning, it looks simple, right? To show this property, it looks very simple. But indeed, when you dig into the core of the computation, you find that you need to show that the ax plus by is a simple random variable. Okay, by the device I gave here. Okay, so you can see once we prove that this linear combination is a simple random variable, then the following calculation becomes too straightforward. Let me say. Okay. Now third one. Oh, so I think let's take a 5 minutes break. Yeah. Oh, sorry. Okay, so let's go to finish the proof of this proposition. Okay, so the third one is that if random variable y always greater than or equal to random variable x, then the same order apply to their expectations. Okay. Okay, so if x less than or equal to y, then y minus x will be greater than or equal to 0. Okay? Greater than 0. And as we know, linear combination of simple random variables are simple, right? So y minus x is also a simple random variable, as we know, and by probability 1. Okay. So the expectation is greater than or equal to 0. So now, y can be written as x plus y minus x. Okay. Implies that expectation of y is the summation of their expectations by 2. So I make a remark. A simple random variable by the argument in 2. Okay. So I will say, maybe I show here. Okay. So that in the proof we show any linear combination of two simple random variables is also a simple random variable. Okay. Okay. So now we have a simple non-negative random variable, and by 1 is expectation is greater than or equal to 0. Okay, and by 2 we apply the linearity, right? So this is the linearity, and because this one is greater than or equal to 0, so that is greater than or equal to ex, and we have done, because this term is non-negative. Okay, so this term becomes a low bound. Right. So when x is less than or equal to y, then expectation y is greater than or equal to the expectation x. So that is the third one. The fourth one. Okay. Since x is equal to ai, indicator of x equal to ai. Okay, so we can express the absolute value of x becomes to I from 1 to n. The absolute value of ai, indicator of x is equal to ai. Okay. But be careful, even though x equal to a sub I form a partition of the summer space. Okay. This part actually, so they are atomic events of these simple random variables, but these events may not be atomic events of this absolute value random variable. The reason is that it's possible that two different A sub I have the same absolute value. For example, 1 and -1 have the same absolute value. In that case, the atomic event would be the union of x equal to 1 and x equal to, so okay. For example, if x may take +1 and -1 as a value, then x equal to 1 is the union of okay. So the atomic event, this atomic event generated by the absolute value of x is actually the union of two atomic events generated by x. So the number of atomic events generated by the absolute value of x may be smaller than the number of atomic events generated by x. This is because that the absolute value of x is a data processed result. So data processing will lose information. This is a general rule. Okay. So raw data is the king. Okay, but may not be convenient for use. So people always do data processing. But once you process the data, you will lose some information. That's a universal rule. Okay, so you have to keep in mind. Okay. So sometimes we say data processing is a necessary evil. Why? For convenience. Okay. But always keep the raw data is the king rule, if you can. Right? Okay, so so that you see, x is this one, right? So now we know AI would be less than or equal to AI absolute value, right? So that means that AI and probability of x equal to AI will be less than or equal to absolute value of AI, probability of x equal to AI. And this implies the summation. So the expectation of x, which is the summation I from 1 to n, AI probability of x equal to AI, would be less than or equal to summation I from 1 to n, and the AI absolute value, probability of x equal to AI. Okay. And, sorry. Okay, and this is expectation of x. Okay, expectation of x, because by this representation. So that's the fourth one. The fifth one, all right, since x is equal to ai, indicator of x equal to ai, and y is equal to summation j from 1 to n, bj, indicator of y equal to ai. Okay. Then x times y is summation I from 1 to n, summation j from 1 to m, ai, bj, indicator of x equal to ai, times indicator of y equal to aiy. Sorry, bj. Now, the product. The product of the indicator of two events is equal to the indicator of their intersection. Okay, it's equal to that. All right, so as an exercise, I may take this as a problem in next quiz. Okay. So the lemma is that let EF be, so maybe I write it here, be two events in the sigma F, algebra F. Then the product of the respective indicator is equal to the indicator of their intersection. Okay, and the proof as an exercise. Okay. Another lemma I have used improve the second statement is that let E1, E2 up to En be disjoint event, okay, in the sigma algebra F. Then the indicator of their union is the sum of their respective indicator. Okay, so that is joint union. If E1, E2, En are not disjoint, then the identity is not true. Okay, so this identity is true only if that E1, E2 up to En are disjoint to each other. Okay, they are disjoint to each other. Okay, so this, the product of these two, because I use the functions, right? Because indicator is still a functions. Indicator just 0 or 1, right? Two values. Very simple functions. Okay, and so this is come to here. So you can see the product. So from here, you will see that, which shows that x and x times y is a simple random variable again. Just like a linear combination of two simple random variables is also a simple random variable. Then the product of two simple random variables is also a simple random variable. Okay, from here, from this calculation, you can see it immediately. Okay, and so by definition of the expectation of discrete random variables, we know that AI, Bj, and because this is indicator of this joint event, so it's the probability of x equal to AI, y equal to Bj. Okay. Now, we apply independence. AI, Bj. Now, because they are independent, so the probability of their joint event becomes the product of their respective probability. So this is AI times probability of things x and y are independent. Okay? Okay. And so you can see, so this is a full product. So you can see that this is AI, probability x equal to AI, times j from 1 to m, Bj, probability of y equal to Bj. Okay? So this is the result of the product of these two sums. And this is expectation of x, and that is expectation of y. And we have done the proof for the fifth property. Yeah. Okay. Last one. Cauchy-Schwarz inequality. Now, things again, AI, indicator of x equal to AI, and y is equal to j from 1 to m, Bj, indicator of y equal to Bj. All right? So the square, what is the square? The square is a data processing, right? We're using the quadratic function to do the data processing. So the result, the value, when the value is AI, and we have taken the square to each value. Okay, and so that AI become to square. And when all the outcome is in this event. Okay? So for all outcome in this event. and the y square becomes to j from bj square, indicate of y equal to bj. Okay. Okay, so from here, it is clear that s square greater than equal to 0 and y square greater than equal to 0, right? So we know this random variable. This random variable is non-negative, and it's also simple, right? You can see, yeah, simple random variable and non-negative. And y square, so they are simple random variables. Okay, and so that implies that their expectation is non-negative. By 1. Okay, so by the first property, we know immediately the expectation of the square of x and the expectation of the square of y non-negative. This is immediate by 1. Now we first assume that both are greater than 0. Okay, we assume both of them are greater than 0. All right, and so we define. So we let x bar a kind of, we normalize. So we divide x by a constant. And because it's greater than 0, so we can put into the denominator. Okay? All right? Which are simple random variables. Okay, 2. Okay. Because linear combination here, but we just scale them. So the simple random variables. Okay. And so okay, and now x now we know this normalized function plus minus another function and take the square, always non-negative, right? This is the perfect. Yeah, we normalize them because we define, yeah, x bar is by divide something, so a kind of normalization. Okay, divide something. Okay, so so this function, you know, x bar is a function, a real value function. Okay, because it's a random variable, right? So it's a function on the every outcome and function on every outcome. So when you add and minus, you take a perfect square. This is always greater than or equal to 0 because their values are real value. Okay. Okay. So that is says that the square. So their square is greater than or equal to 2xy here. So this implies that 2 x y bar absolute value. So it can be plus, no matter which sign you take, this is always upper bound, so that you take the absolute value, you get the same result. Okay, so you have that. Now, so everything here is from not in probability, just about real numbers. Okay, about real numbers. And now we take the expectation. Okay, so expectation. Okay. Okay, maybe I by the third property. Okay, and this is by 2. Okay, by linearity. But what is the reason why we do that? We do this. It's because that so we look at that. This is x and expectation square plus y. Okay, because when you square this one, the numerator is x squared and the denominator is expectation of the x squared. So, and by linearity, this is divided by this one. Okay, so this constant can move out by 2 again. Okay, by 2. Okay, that's a scale, and so you can move the denominator out of the expectation. So that is 1 over something. Okay, and so that is 1 plus 1, and this is 2. This is the reason why I call it normalized. Okay, and what is this? This is equal to 2 again by by 2 again. So you can move the coefficient out of the expectation. Okay, so this is property 2. All right. So that okay, so when the expectation of x bar, y bar will be less than or equal to 1 if divided by 2. All right, but what is that? This is x square root of expectation of x squared and y divided by expectation of y squared absolute value. Now you can, by property 2, so you have expectation of x, y. And here you have E x square, E y square, less than equal to 1. So this is by 2 again. So you can move the constant out of the expectation. So get this one. And so you get and finally when you take the square, you get upper bound. Okay, so that is the last one. Okay, complete. Okay. Any questions? Okay. Now, so for a non-negative random variable x, there is an increasing sequence of non-negative simple random variables x1, x2, such that the limit of xn is equal to x omega for all x by proposition 5.2.c, right? So we have such an approximation. Okay. Right now, by proposition 5.2.d dash, the third property, we know that expectation of so we have a monotone increasing sequence of non-negative numbers, right? We have that by and 2 and by 1 and 3. Okay, the first one is from 1, right? And the rest inequality from the third property. So we have a monotone sequence immediately. And so we define the expectation E of x as here the limit of this monotone increasing sequence of non-negative numbers. So this is the definition. So it's very convenient, right? You can see, because we can always approach a non-negative random variable by quantization. Quantization is one of possible way to approach this non-negative random variable. There are many other approaches, but quantization is one of them, as I demonstrate in proposition 5.2.c, right? I demonstrate that. And so anyway, so I give this definition, but is that a well-defined definition? Because you have to, so I have to raise a concern. So one, all right, I think and this is a fundamental about the above definition. Okay, is that whether the limit value is dependent on the approximation sequence xn chosen. So the question is that if we choose different approximation sequence and take the limit of their expectation, will they have the same limit? Okay, you don't know at this moment, right? So this is a big concern, even though the definition is convenient and computable, right? Because I have demonstrated by using quantization, right? You can compute, you can do the x1, x2, and then you can compute the expectation. Okay, and the resolution can be very high. Depends on the bits you want to put on, right? And actually, it's the n-bit resolution. Okay, because if n is 1, the resolution is half, 0.5, so it's 1 bit. But n is 2, the resolution is 1/4, so that is 2 bit. Okay, so as the number of the resolution, the precision increase, then we will approach to the non-negative random variable very well. And if this work, okay, then you can approach to the expectation of x, right, by computing the expectation of these simple random variables in computers. All right, so it's workable, but we have to resolve this concern. And So I think at run out of my time. So it will be proved that the limit value is independent of the sequence chosen. Okay. So okay, and so we will prove the lemma stated in the textbook, but the textbook gives a very limited proof. I will give you a general proof for any non-negative random variable x. The expectation of x is actually this integral, and it's actually 1 minus the CDF of x. So when I put the index, the subscript here to indicate that this is the cumulative distribution function of the random variable x. Okay. So I'll show to you that this definition end up with this formula, and you can see that this formula depends only on the distribution function. Okay. So once we prove this lemma, then because for any, even you have a different approximation sequence, the value is the same as this one. Okay, and this one you can see depends only on the CDF of the random variable, which is unique. So we settle. So once we prove the lemma, we settle our concern. Okay? Right. So next week I will prove this lemma in a general setting. Okay. All right. So I stop here. Okay.